Hi again. In this part of the presentation, we're going to do some experiments to find out what the AC and DC characteristics are of the probe, the transfer characteristics. But firstly, we're going to look at the DC characteristics, and so let's just pull this up. And so we're looking at this when the probe is in ×1 and also in ×10 mode to see what effect it has on circuits and how important it is to understand what's going on so that you can actually choose whether it's a ×1 mode or a ×10 mode that you actually want. So first of all, we're going to actually look at the simple formula associated with voltage division. And this is like a level 1 degree type electronics where this is the standard voltage divider equation where you've got a resistor R1, another resistor R2, and these are in series, and actually you've got V in here, V out here, and you're looking at the relationship of V in, V out, V in, depending on what's going on with these resistors. So the formula is V out is equal to V in times R2 divided by R1 plus R2. And this can be rearranged such that R2 is equal to R1 over V in over V out minus 1. So this formula may well be familiar to you, but if not, don't worry about it. I'll mention it later on, and it's all written down, but you get a rough idea of what's going on and how important this is. So here we have a circuit for testing the DC transfer characteristics of our probe. Now, I've got a power supply here, which is 9.8 volts. The reason for choosing 9.8 will become apparent in a minute. It seems a bit of a strange number, but there was a reason behind it. And here we have a series of resistors. We've got 1K, 10K, 100K, 1 meg, and 10 megs. And we're going to have some test equipment here in a minute. But ideally, your test equipment shouldn't change any of the characteristics in your circuit. Now, so ideally, if this was a perfect piece of equipment, it would have no load resistance. I would have an infinite load resistance, so it didn't affect your circuit, which means that in this condition, if I put my test equipment across here to ground, then because this has got an infinite impedance, therefore there's no current flowing through here. Therefore, the voltage here is the same as the voltage there because there's no current flowing, and that's our ideal scenario. However, in reality, that's not what happens, and this is why it's important to understand this. So here we have a simplified version of what's going on with the probe here and the PicoScope. Now you'll see I've set the probe here with a resistance of 360 ohms, and that's because that's what I measured. If I got a multimeter and I took a resistive measurement between the tip of the probe and the pin inside the BNC connector that we discussed earlier, and that resistance is approximately 360 ohms. So this is just an approximation of what's going on, because it's not just a simple wire that goes from the probe tip through to the BNC connector. So there's our 360 ohms, and also inside the PicoScope there is actually a 1 mega ohm resistor across the input. And it's important we actually understand what is now the impact of all of this on this circuit. And here I have a circuit with the 1K, 10K, 100K, 1 meg and 10 meg resistor. These are around about 1% resistors, these ones here. And I'm also going to connect my scope probe ground to my common ground of my circuit here, and I'm also going to connect the hook tip to the power line of this circuit like that, which is the power bus here, and I've got a power supply that's generating around about 9.8 volts. So here I've pulled up the mean of the voltage. This is from the measurements. If I go to more, you'll see the measurements bit here. So what I've done here is actually pulled up the mean of the signal, and let me just check my probe is on ×1. So I'm just going to double check that everything's okay, because I do a lot of setting up with this. So there's my probe, it's on ×1, and the vertical is on ±10, and you'll see here that we've got around about 9.8 volts. Now what's important is what happens when I actually move this probe around my circuit. Now, ideally, we don't want it to have any influence at all, because we should always see 9.8 volts. However, that's not actually what happens because of the nature of the probe and the nature of the PicoScope itself. And so what I'm going to do now is I'm going to measure and monitor this voltage here as I move it around my circuit. So this is my power supply going in, which is around about 9.8 volts. And I'm going to move my scope probe and I'm going to put it to the other side of my 1K resistor. And now you can see it's just dropped a teeny weeny bit, and it's now like 9.79, 9.8. But as I now move this probe further down my circuit, so this is now the 10K resistor, we've now got 9.72 volts. If I move it down to the 100K, we've now got 8.9 volts. Move it down to the 1 meg, and we've got 4.9, which has really significantly affected it. And at 10 megs, we've got 0.88 volts. So as I've moved my probe through this circuit with different resistors, the signal's been significantly affected. So let's have a look at what's happening. So let's go back to our presentation. So this is the test we've been doing, and I've tabulated those results. And you can see that there's our supply voltage of approximately 9.82. I did fill this in earlier on, so these numbers may vary a little bit from what we just went through, but it's just to get the table done. So when you monitor at 1K, we see the voltage is being seen by the PicoScope, which is fundamentally at this point here is 9.81 volts, and then similarly at 10K we've got 9.72, 100K 8.93, 1 meg 4.93, and at 10 megs we've got 0.9. So this probe and PicoScope, and particularly the PicoScope, is actually interfering with creating a voltage divider network. And it's really important to understand this, because when you come to measure in DC circuits, then the resistance of your test equipment, i.e. the impedance of your test equipment, does have an effect on your measurement. So what we can say from this is that if we use the voltage divider equation, we can actually try and calculate actually what the theoretical value is from these results. So R2 is equal to R1 over V in over V out minus 1. So if we plug in some values here, now R1, I'm trying to find the voltage at this point here, which is the bit that's actually going into the PicoScope itself. So I'm going to take the 10 meg resistor, so we've got 10 megs, plus the 360 ohms that we've got in here, so that's that number here, divided by our voltage supply, which is 9.82, and divided by the output voltage at 10 megs, which is 0.9 minus 1, and that gives us approximately 1.009 megohms, which actually is really good because that's actually what's inside the PicoScope. So through this theory, we've demonstrated that we can show that the input impedance of our PicoScope is actually 1 meg. So this means that in ×1 mode, then you have to understand that when you attach a probe and the PicoScope to your circuit, you do actually influence the circuit. And therefore it may change the characteristics of your circuit because you've got a probe in there. And what we need to do is actually find out, well, if that's in ×1, then what happens in ×10? So let's actually do that now. So we're going to change this, and this is the ×10. Now in a ×10 probe, it switches in 9 meg resistor. This gives our 10:1 ratio here. So what we're going to do is do the same test all over again, but we're going to change our setup. And I'm going to change the probe to ×10 and make sure the vertical is still on that. And what I also want to do now is show you what I'm doing. Let me put my probe back onto here. And so there's my voltage going in here. That's my bus bar on the top bar there. Right, so we're now on the ×10 probe, and here is the voltage at around about 9.8 volts going in. And what I want to do is now I'm going to record that. That's my main power supply going in. Now if I go to the other side of my 1K resistor, you'll see that that hasn't really changed, which is good. I'm now going to move this to my 10K resistor. and you'll see it's just dropped a little bit here to 9.8 volts-ish. And now on the 100k, and we're now on 9.7. On my 100k, we're on 8.9, and on my 10 meg here is 4.9. So this is quite a significant difference having it on times 10. So let's look at the tabulated results for this. So let me just go to this screen back here. So I've tabulated those results. And so at 1k we had 9.83, which is great, and all the way through down to 10 meg. So what we see here is by putting our probe on a times 10, we've got a much larger impedance now, and therefore it doesn't load this circuit in quite the same way. And so that means that we are, by putting our probe on times 10, we have less of an impact on our circuit from a DC perspective. And so once again, if we're going to use a choice between times 1 and times 10 when it comes to DC circuits, then unless it's very small signals, then we'd certainly recommend going to the times 10 mode, because you'll get a better response because your probe and oscilloscope are not interfering with the circuit in the same sort of way. And so that's it from a DC perspective. We're going to take a break now, and then we're going to look at it from an AC perspective in the next video.